Hello everyone, I'm Norman Wabiger. Today we're going to be looking at three important patterns which are tilings of the plane. This is a very big subject, tilings or tessellations, which actually has a lot of practical applications, connections with art, architecture, and even just tiling the bathroom wall. But for young people, I want to focus your attention on three particular sort of patterns which are sort of crucially symmetrical and important in the subject. So they're sort of the starting point of a wide discipline. Okay, so we're talking about a tiling, which is what? Well, it's roughly a subdivision of the plane, or maybe part of the plane, into disjoint polygonal pieces, or polygons. And these pieces will be called tiles. So here are two examples. Okay, so here is rectangular tiling. We see these little polygons, which are actually rectangles, and they fit together to form this pattern. And even though I've only shown part of it, you can see that this pattern could be extended, right? We could extend it in this direction, or this direction, or in this direction, or this direction. And so, theoretically, at least we could extend it as far as we want it. There's an identifiable pattern here. Here's another one where the tiles are equilateral triangles. And some of them are sort of right side up with the base horizontal, okay, like the red ones that I've colored. And then there are the other ones which are kind of inverted like this, with the horizontal being the top. So here we have equilateral triangles, here we have rectangles. These are both tilings. You could imagine extending this indefinitely in either direction. Here we've added something extra. We've added some coloring, okay, making it even a little bit more interesting. And in fact, that's what happens typically. You have an ordinary tiling like this, then you can sort of augment the discussion by asking, well, how could we color this in an interesting way that preserves some of the symmetry of the situation? So we want to talk about this general framework here, and it's a very rich subject. So this is just an introduction to tiling. And it's a really nice subject for primary school students because it can be illustrated with very simple diagrams that they can appreciate. There's something aesthetically pleasing about the regularity involved here, the fact that these simple pieces are fitting together nicely. And these are things that students can interact with. They could actually make something like this out of little rectangular or triangular tiles. They could put them together in different ways. They could come up with original patterns of their own. So it's a very nice topic, and it has a pleasant geometrical aspect, which complements all the arithmetical work that we've been doing. So we want to have a balance in mathematics and in mathematics education. We don't want to be just drilling arithmetic, important though it is. We want to balance that with some geometry, and then later on with some other things as well. Now, historically, the story of tilings goes back many thousands of years because artistic decoration of walls, temples, pottery, jewelry has been around for a long time. But for example, we could go back to the reign of King Djoser in ancient Egypt, one of the very first important pharaohs who built the Step Pyramid, which is really the precursor to the great pyramid building that occurred in just subsequent generations. He lived around 2600 BC, and in one of the funerary apartments underneath the Step Pyramid, you can find a wall which is decorated in a very pleasant fashion with a tiling consisting of, well, mostly these rectangular blue tiles. And there's quite a lot of them, maybe 15 or 20 in either direction, and sort of interspersed with these rows of decorative smaller rectangles. Okay, so that's obviously something kind of geometrical, a pleasant pattern that looks nice. On an Akkadian victory stele, so this is going over to Mesopotamia, a little bit later, 2200 BC, there's a statue which has a very pleasant pattern on it, which we look at and we can sort of see a tiling there in terms of these squares arranged in a pleasant, actually curved pattern along the statue. Now, these are just two examples. You could choose a lot of examples from antiquity. So the Persians, the Greeks, the Romans, they all used these kind of patterns in decorative art and architecture. And I think it came to a kind of a high point with Islamic art. So in Islamic art, there's a disinclination to represent actual figures, and so the elevation of abstract pattern motivated art became very, very beautiful. And we will hopefully have occasion to describe some of the remarkable things that we find there. But these are somewhat more advanced. Today we're just going to broach the subject by looking at some very simple examples. Now, of all the many, many tilings that are out there, the simplest ones are the regular tilings, the ones that have a lot of symmetry. So a regular tiling is one where each tile is itself a single regular polygon. There's only one type of tile, okay, that's used throughout. And it has maximal symmetry. And we'll explain what that means in a second. And we also want this tiling to extend to the entire plane. So even though we're only picturing it typically in part of the plane, we do want it to, extend in an obvious way further and further out. Now, of all the various tilings, the simplest one is almost surely the square tiling, okay, which is one that we've seen already. It's the grid plane or a piece of graph paper, okay, very simple and important. So it's created by two families of equally spaced parallel lines. So here's one family of equally spaced parallel lines, and here's another family of equally spaced parallel lines, and the separation between any two adjacent lines here equals the separation between any two adjacent lines there, and so we get this pattern of squares. Now, there is one of the tiles in this tiling. It's a square, okay? And if we look more carefully at it, we see that these squares sort of fit together in a nice way, and it's nice to say something about how they fit together. So if we look at a vertex, a point where two of these defining lines cross, say that one right there, then we see that at that vertex there are four tiles, four squares that are arranged around that vertex. So besides the red one, there's also this one here, and this one here. So there's four tiles around a vertex. And of course, that's not just true of that vertex, it's also true of that vertex, and any of the vertices. Okay, and then additionally, this has a lot of symmetry. Now that's a very important concept that we're going to have to talk about more. But at this point here, let's just note that there's a kind of obvious translation symmetry, right? If we take this pattern and move everything over by sort of essentially one square, then the pattern is imposed upon itself. You couldn't tell that it's actually been moved. Now that's not exactly true if you just choose a finite portion of it, like this. Like if we just chose this thing here and moved it, you'd be able to tell that I moved it because it'd be in a different position. But if you think about this as being sort of part of this pattern that carries on, then moving it is not going to really essentially affect it. But there's also other kinds of symmetries. For example, there's reflection symmetry. We could take the whole story and reflect it around, say, one of the vertical lines. Reflect it. Then the pattern is mapped back onto itself. Or one of the horizontal lines. Similarly, we could reflect. In fact, there's other kinds of reflections also, okay, which you might like to think about. For example, there's also reflections through lines which are sort of halfway between adjacent lines in the ruling. So if we use this as a symmetry axis, there's also a symmetry there. In addition to the translation and the reflection symmetry, there's also a kind of a rotational symmetry. Okay, so if we choose a vertex, let's say that one there, we can imagine rotating the entire grid by a quarter of a turn. What do I mean by that? Okay, so here is a rectangle, and let's say I want to rotate around the center. Okay, so a quarter of a turn, I mean like that. That's a quarter of a turn. I do another quarter of a turn, I get to that. I do another quarter of a turn, I get to that, and one more 1/4 of a turn, and I'm back to where I started. So those four rotations, each is identical. When we compose them, we put them together, we get 1, 2, 3, 4. We get back to where we started. Okay, so that's a kind of a symmetry that this pattern has. If we choose one of these vertices and rotate by a quarter turn, then all the squares map on top of other squares, and we can't really tell that we've moved the entire thing. So even a very simple pattern like this has some actually quite subtle properties when we start looking at it from the point of view of symmetries. That's a very rich subject that we're going to be talking quite a lot about. Okay, it's actually a very accessible and pleasant, and I think it's a nice topic for young people to learn about. Now, the second really important tiling is the equilateral triangle tiling, which is given here. Okay, this is created by three families of equally spaced parallel lines. There's this family here, and then there's this family here, and then also this family here. And it's a little bit more subtle than the square one. So these ones sort of fit together, but it's crucial for this kind of pattern that there's a certain particular relationship between, say, these lines and the horizontal lines. And the relationship actually is that going from here to here is 1/6 of a full turn. Okay, with a rectangle, or a square, it's 1/4. Here it's 1/6. You can see that because, let's say, if we're looking at things from this vertex here, going from here to here is the same as from here to here, from here to here, and here, and here, and here. There's 6 of them around that central vertex. Okay? Reflecting the fact that in this case there's 6 triangles which are arranged around any vertex. Okay, so the tiles are in this case equilateral triangles, and 6 of them meet at a vertex. And here also, as before, there are various types of symmetries. There's a translation symmetry. Actually, there's quite a lot of translation symmetries because we can move things sort of in this direction, or we can also move things up. We can also sort of move things along sort of these kind of diagonals appropriately. There's quite a lot of symmetry, but it's a different kind of a family of symmetries than in the square tiling. And there's also rotational symmetry, and there's reflection symmetry as well. And there's quite a lot to say about that, so we will be investigating that a little bit more once we learn more about symmetries. But just at this point, we recognize that it's a highly symmetrical situation. Very pleasant because of that. Now, the third and final tiling in our list of regular tilings of the plane is the regular hexagon tiling. And it's almost surely less familiar than the other two. In this case, it's based on the equilateral triangle tiling. So it's a kind of a derivative of the one that we've just looked at. And in fact, you can see that I've created it here by superimposing a black pattern on top of that blue pattern, which was the equilateral triangle tiling. So the black lines create these tiles which are regular hexagons, like this one here, okay? 6 equal sides. And if we look at a vertex, say that one there, we see that there are 3 hexagons which meet at that vertex. This is also a very pleasant situation, which also has obvious sort of translation, reflection, and rotational symmetry. And maybe from a certain point of view, this is actually maybe even the most regular of the regular tilings. Why is that? Well, because if we look at it from the point of view not of a vertex, but of a tile or a face of this tiling. So let's say we look at this tile here and ask, how many tiles are touching this one? Well, it's easy to count, right? So we're looking at the tiles that touch this one. Well, here's one, here's a second, here's a third, here's a fourth, there's a fifth here that I've only shown half of, and there's a sixth one. So there's 6 tiles around this central red tile. Now, consider how that relates to the, say, square tiling. In the square tiling, we had a situation like this, okay? Something like this. And so suppose that we are asking the same kind of question about, say, this particular square tile. How many square tiles are around that one? Well, it's a little bit more subtle because there are actually a couple of different kinds of tiles that are touching this red one. There's this one here, which is sharing an edge with the red one, as is this one, as is this one, as is this one. So these four are directly touching the red tile. But then there's also these sort of corner ones, like this one, this one, this one, and this one, which are also actually touching the red tile, but only at a corner. But still somehow they deserve to be considered some kind of neighbors, right? If this was your house, you could hop the fence to get to that neighbor, but you could also hop the fence sort of diagonally to get to the green neighbor. It's also a neighbor of yours. It has a sort of a different role than the black ones do. And if we look at the same story, say with the equilateral triangle situation, which I can just do up here. So let's just say consider this particular tile in the equilateral triangle story. Then how many neighbors does it have? Well, it has sort of three direct neighbors that share a face or an edge with it. But then there are these other tiles which you could get to from the red one, namely this one, this one, this one. You could hop, over the fence from the red one to any one of these green ones. And then there's also these three, and there's also these three. So actually there's 3 plus 3, 3, 3. There's actually 12 sort of neighbors of the red tile in the equilateral triangle story. Here there's 3, 6, 8 neighbors of the red square tile. But here in the hexagonal story, each hexagonal tile has exactly 6 neighbors, and they are all sort of on the same footing. There's not sort of closer neighbors and not quite so close neighbors. So that's a kind of an additional regularity that this particular hexagonal tiling has. So even though it's the least familiar of the tilings, it has some claim to being perhaps the most interesting one. So we had a look at these 3 important tilings, and they are mathematically important because they are, in fact, the only regular tilings of the plane. And in that case, what do we mean exactly by regular tiling? Well, let's put it this way. That first of all, each tile is a regular polygon, okay, and they are all congruent. So we're using the same fundamental shape, which has to be a regular polygon. Okay, repeating that one shape all over the place. Secondly, the tiles are arranged edge to edge. So when we have 2 of our tiles which are adjacent so that they're sharing a common boundary, that they do so sharing the full edge. So that's different from the brick tiling that I showed you at the beginning. Remember that was sort of, had some rectangular bricks like this, and then the one on the row above it was like this. This is not an edge-to-edge tiling because this tile and this tile are touching, but they're not sharing an edge, okay? So the relevant edge of this one is that edge there, and the relevant edge of the top one is this one here, and they're not being shared. They're overlapping, but they're not identical. So if we exclude that kind of thing, we want the tiles to really touch coherently and fully, then that's what we mean by an edge-to-edge tiling. And then there's the question of symmetry. We want this to be sort of maximally regular or symmetrical. And one way of saying that is that all the vertices look the same, all the edges look the same, and all the tiles look the same. And you can think about that as meaning the following, that if you were at one vertex, sitting there at this vertex, and you're looking around and videoing what you see, you're taking photographs and so on, then what you're going to report is exactly the same as what somebody else is going to report standing at a different vertex. Right? So the way things look at one vertex is exactly the same as the way things look at any other vertex. And that's true not just for vertices, but also for edges and also for faces. So this is kind of symmetrical at the level of vertices and edges and faces. Okay, so it's a very strong kind of regularity. And when you impose those conditions on a tiling, then it turns out that 3 that I've shown you are exactly the only regular tilings. So mathematically, they have a kind of a primary place in this pantheon of tilings. Okay, so these three tilings are mathematically kind of important, but why should some primary school students study them? So first of all, they are simple and elegant, and they do actually have a very rich history, going back to at least Kepler, who explicitly sort of studied them along with three-dimensional kind of versions. They generate lots of further tilings and coloring. So once you have a square tiling or an equilateral tiling or a hexagonal tiling, then you can do other things with it. You can subdivide things further. You can create additional, maybe more complicated tilings. And you can also ask lots of questions about colorings, and you can color these things in pleasant and interesting ways. Of course, the square tiling has a kind of an independent fundamental importance because it's really the essence of Cartesian coordinate geometry. I mean, that's the setup with x and y axes and a piece of graph paper. They're really pretty well the same thing. And the other two, the equilateral triangle and the regular hexagon tilings, suggest that maybe there's other geometries, floating around that, maybe are kind of comparable to the Cartesian geometry that is basically set up from the square tiling. So the existence of these other two tilings, I think, broadens our mind a little bit about, what geometry might be. I think that's a very interesting topic, which we will be talking about a little bit more later on. There are some additional reasons as well. There's also the other reason that was on the previous slide that I didn't talk about, that many board games, in fact, use these tilings to move pieces around. And a really great example of that, at least from my personal experience, is that when I was a teenager, me and my friends played these board games that simulated campaigns in like World War II. And there was a wonderful company called Avalon Hill that produced these very rich and beautiful recreations of these campaigns. And I remember getting a game called Anzio, which reconstructed the Allied campaign to win back Italy in World War II. And anyway, one of the interesting aspects of this is there were all these sort of pieces that corresponded to divisions and regiments and so on. But they moved around on a hexagonal board. So in other words, a board whose tiles based on the hexagonal pattern. And that's kind of actually quite a pleasant thing, because there's a richness about that you can move not in four sort of adjacent directions as in the square lattice, or in three adjacent directions as in the triangular lattice, but actually in six adjacent directions. So if you want to simulate movement with maximum flexibility still in a kind of a symmetrical and rich way, the hexagonal lattice is very useful. Okay, but some other applications. Well, first of all, these tilings occur frequently in art and architecture, so that's very nice. And they also naturally lead to the 5 Platonic solids. So once we've understood these 3 tilings in the plane, then it's not a big step to ask, what are sort of 3-dimensional versions of this? And that naturally leads to the 5 Platonic solids, which we will also have a lot to say about, which is also another rich geometrical topic that primary school students should see and interact with. So this is a precursor to that. And of course, they have very rich symmetries because, well, we've explained already, there's translation symmetry, reflection symmetry, rotation symmetry. So these tilings are great sort of laboratories to teach young people about symmetries. And I'm going to be going in that direction, so we're going to be using them as a springboard to explain things about symmetries. Now, before we talk about what's going to happen next time, I do want to pose this sort of intriguing question that maybe has occurred to some of you. So the question is, what about the regular pentagon? The 3 tilings that we've used so far are the square, the equilateral triangle, and the regular hexagon, with 4 sides, with 3 sides, and with 6 sides. But what about the tile with 5 sides, which is regular, the regular pentagon? Shouldn't that also be the cornerstone of some nice tiling? Well, it turns out that the number 5 is crucially quite different in this role than the numbers 3, 4, and 6. And that's a very rich story, which has all kinds of interesting, ramifications. Ultimately, I suppose in modern times, leading to the famous Penrose tiles, which is a kind of a way in which the pentagonal story ends up still giving you tilings, but in a more subtle, much more subtle way than these regular tilings over here. Okay, so great, we have an introduction to this idea of tiling, and we've introduced this idea of symmetry. Very important concept, even for primary school students to get their heads around, emphasizing the geometrical side of mathematical thinking. So symmetry is a great thing to learn about, and we're going to be investigating that more. So we're going to start talking about that next time in the context of a mirror symmetry, which is arguably the simplest kind of symmetry and a starting point to investigate the rich symmetries behind these tilings that I've shown you and a lot of other ones as well. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.